So we're talking about this problem. Have we done this? So yesterday we discussed about the shunt DC generator, right? And this problem says that the generator is generating at a speed of 1200 RPM, right? And the parameters are given: RFW 30 ohm, R8 0.2 ohm, NF 200 turns per pole, PR 1200 watt. The demagnetization MMF is 50% of the load current, and the external field resistance RFX we need to find, and then we need to find the terminal voltage, the voltage regulation, and the efficiency. So first we need to find the terminal voltage. So I told you last class that in order to find the terminal voltage, it is an iterative process. We need to follow that iterative process, then only we'll find this terminal voltage, right? Like the terminal voltage develops, it is also iterative process how it develops, right? Yesterday we discussed it, right? So now considering this no load voltage as 170 volt, can you find the RFX? So this is your magnetization curve, right? So with respect to 170 volt, I'll find the current. It will come around 3.5 ampere from the magnetization curve, okay? And if I'll divide it, I'll find the net resistance of the field. That includes the variable resistance or external resistance, RFX. Now the field resistance is given, right? That is 30 ohm. The net resistance we found from the magnetization curve, right? That is 48.57 ohm. Now if I'll subtract the field resistance, that is 30 ohm, right? Then I'll get 18.57 ohm. That is the external resistance connected to the field circuit, right? Okay. So now we know that terminal voltage is, what is the equation of terminal voltage? Can anybody tell? EA minus IARA, right? So this terminal voltage is also, it is across the field, right? So I can write Vt equal to IFRF also, right? Okay. Now the load current, full load current is 100 ampere. It is given in your question, right? And so what is the demagnetizing effect because of the armature reaction? It is 50% of that. So it will be 0.5 into 100. So it will give me 50 ampere turn per pole. So this is the demagnetizing effect, right? Now I have to find the effective MMF, then I can find the, okay. So now in the first iteration, what we do, so EA is 170 volts, right? And the field current we found 3.5 ampere. So the terminal voltage, now I can find it, that is 170 minus 103.5, right? Into 0.1, because your IL is 100 ampere, right? It is 100 ampere IL, okay? So and your field current is 3.5 ampere, right? Now if we'll add 3.5 plus 100, that will give me IA, armature current. So your armature current now becomes 103.5, right? So now your terminal voltage will be, in the first iteration, it will be 170 minus 103.5 into 0.2. That will give me 149.3 ampere. Sorry, it will be volt, right? It is volt. Okay. Now in the second iteration, corresponding to this voltage, right? Now I need to find IF2. Okay. So net IF2 I will find corresponding to this voltage, that is 149.3. So then IF2 will be 149.3 by 48.57, which is the net resistance in the field, right? Okay. That will give me 3.07 amperes. Okay. I don't know whether you can imagine or not. Just let me draw it. So this is your generator where we have field here with resistance, right? And here we have load, right? Okay. And this is your IL, IF, this is your IA. Okay. Okay. Now the terminal voltage we found in the first iteration is 149.3, and this whole resistance across the field is 48.57. So if you divide, you will get 3.07 ampere, right? Now the effective field current, how I will find? By reducing the demagnetizing effect. So the net MMF will be 200 turns into 3.07, right? Minus 50. So that will give me the effective ampere turn in the field. Okay. And divided by 200 will give me the effective field current. Okay. Now corresponding to this field current from the magnetization curve, I can find again EA, the open circuit voltage or no load voltage, right? So that is EA2 will be equal to now 165 volt. Okay. So now the terminal voltage I can find, that is in the second iteration, VT2 will be equal to 165 minus IARA, that will give me 144.4. We can see the variation. First iteration we got 149.3. whereas in the second iteration we are getting 144.4 volt, right? There is a 5 volt difference. Now in the third iteration, similarly, taking 144.4 into account, I will find IF3, the net field current, and then I will find the effective field current considering the demagnetizing effect because of the armature reaction. So that will give me 2.72 ampere effective field current. Okay. Now corresponding to 2.72 ampere, I will now find the no load voltage from the magnetization curve, that will be 163 volt. Okay. Now again I have to find terminal voltage VT3, that is in the iteration 3. So I will find it, then I will find it is coming to 142.4 volt. Now if you will see the mismatch of the voltage, that means error in the voltage, that error is coming around less than 2%. So now we can consider this. Even in the, you will go to the next iteration, you will find around 142.4 volt in the next iteration. So therefore we will not go to the next iteration, we will converge here, that the terminal voltage we'll consider is 142.4 volt, right? Now your terminal voltage we are considering 142.4 volt, and your IF from that will be 2.93 ampere, right? And IL we know 100 ampere, and your IFE, that is effective field current, from this I'll find 2.68 ampere. Then again EA will be 163 volt. Same voltage will come, right? Now we can find the voltage regulation. So voltage regulation is your no load voltage minus full load voltage, right? Full load terminal voltage we found around, it is 142.4, right? And this is your no load voltage, right? 170. So therefore it will become 19.39%, 38%. Okay. Now the third part is your power output or efficiency we need to find. So before going for efficiency, we must know the power output. So power output is nothing but it is equal to VT IL, right? So IL is 100 ampere and VT is 142.4 volt. If we'll multiply, we'll find output power, right? Okay. Then we need to find the losses. So already rotational loss is given. We need to find the copper loss. So copper loss we have to find by just multiplying the current square into resistance. The resistance values are given here, right? So in the armature circuit we have this much of copper loss. In the field winding this much of copper loss, right? So now we'll find the net copper loss, and then we can find PD as P in just by adding all the losses into the output, and this is your P in. P input. Now efficiency will be P out by P in, that is coming around 79.22%. I hope everybody understood this problem. Okay. In the exam, if such problems will come, you can do it, right? Okay. So we have completed the shunt connected self-excited generator. Now I'll talk about the series connected self-excited generator. So in the shunt connection, we have seen the field circuit was parallel to the armature circuit, right? Now in this type of generator, your field circuit, whatever you are seeing here, right? This is your field. This is actually connected in series with the armature. This is your armature. This is your field, right? Now they are connected in series. And we have here one diverter, we call it diverter resistance, which is required to maintain the flux in the field circuit. Okay. So in order to maintain because this will help to control this current IS in the field circuit. IS is the series field current, and that will help us in controlling the current in the series field winding, right? And this is the load, right? Okay. Now, what are the governing equation? Can you write it? Just tell me, I'm writing it here. So if I'll consider the governing equation, I can write EA equal to VT plus
IARA
ISRS. Okay. Or you can say IS is equal to IA minus ID. Okay. IS is equal to IA minus ID. Right? Okay. Now, these are the governing equations of yours. It is very, very easy, right? Now the question is, if I'll remove this load from this circuit, what will happen? Can it produce voltage? Like in case of shunt generator, we have seen that when even the open circuit also it produces the voltage, right? Because the whole armature current passes through the field, right? Now here in this case, can it produce voltage? It cannot produce. So therefore this external characteristic of this kind of generator is completely different from that of shunt generator or separately excited generator. Okay. Now, so we'll see how it looks like. So this is your characteristic, external characteristic. Okay. I hope this is visible to all of you. In the back side also. Visible backside? Okay. Okay, so now you can see this this characteristic without the armature reaction or drop, if we'll see, when the load current is 0, obviously the voltage is 0. Will the voltage be 0? Huh? No, it will not be 0 if some residual flux is there. So let us say some residual flux is there, so then it may start from here. Okay? But the voltage will be very less. Now as soon as the load is connected, so it will start developing the voltage. Okay? With that residual voltage, it will supply the initial current to the load, then it will start developing the voltage, right? So gradually it will develop. So your terminal voltage therefore will completely depend upon the load current, unlike in case of shunt generator, right? So therefore it will start developing and it will just increase. And if we'll consider the armature and field resistance drop, this is your drop, and the armature reaction drop is here, and if we'll reduce the voltage by that, then it will look like this, right? So this is your characteristic, or you can say external characteristic of the series generator, right? Generally, what is then the question may be arise in your mind that what is the application of this kind of generator? Is it useful really? Because in the beginning there is no voltage, we cannot use it, right? Unless the load is connected, it cannot have the voltage, right? It has a specific application where we want to boost the voltage. At that point we can use this and we can get the boosted voltage, right? So how we can boost the voltage, we'll see in this example. Okay? How we can boost the voltage using the series connected or series generators, right? So now we have a feeder, we have a substation. Okay, let us say this is a substation having a source. Okay, now it is feeding to some load at the other end. This is the load. Substation, you know, substation means? Have you seen substation? Huh? Where you have seen? Huh? Where?
Many places.
Where? Can you identify one place?
The T blocks.
Just beside your hostel there is a substation. Huh? The main road when we come near the barber shop, right? And again if we'll go back to your hostel, there is a main substation where we are connecting 11 kV. The 33 kV is coming. 33 kV feeder is coming, and where it is converted to 11 kV. Then 11 kV is being circulated around the campus. Okay? And again we have many small substations which converts 11 kV to 440 volt. Okay? Now, this is a substation where it is feeding the load, and this is the feeder. You can mark here. And there is a series generator which is having EA equal to 0.4 IS, and the generator has RS equal to 0.03 ohm, RA equal to 0.02 ohm. It is used as a booster between a 240 volt station, bus bar, and a feeder of point. So feeder resistance is 0.25 ohm, right? Calculate the voltage between far end of the feeder and the bus bar at the current. Bus bar at a current of 300 ampere. So this is supplying 300 ampere. Okay. Now, the series generator is connected here somewhere. Okay, it is connected here, let us say. And here we have the field winding or something else, right? So then this is your substation with some voltage, right? And Okay, it is 240 volt substation. Okay. So series resistance is 0.03 ohm and RA is 0.02 ohm. Okay. And feeder resistance is given here. Calculate the voltage between the far end of the feeder. That means voltage. What will be the voltage here? The current is 300 ampere, right? Now I hope you understood the concept of the problem. If you are clear, the concept is clear, you can go ahead, right? So your EA is 0.4 IS. So now IS is equal to the load current. The load current is 300 ampere, it is mentioned, right? Now EA will be 120 volt. Okay? Now the voltage drop across the resistances, that is 300 ampere into 0.02 plus 0.03 plus 0.25. So this 90 volt drop is happening throughout the feeder and the resistances in the generator, right? Now the voltage between the far end and the bus bar will be 240 plus 120. 120 is the EA, right? 240 was the substation voltage. 240 plus 120 minus 90 is the voltage drop. So this is the voltage across the terminal. Sorry? What is telling?
Generally 190 minus.
It is coming 190.
How? 120 add to
Oh, 120 क्यों ऐड हुआ? That is your question. Huh? Oh. 120 is the voltage. I told you, na?
Yes.
The generator is in series with the substation. Huh? What?
Voltage drop होगा.
Voltage drop is here in the resistance, right? Voltage drop is here. We are finding the terminal voltage which is connected to the load. Voltage drop is here in this area. Okay? Clear? Yes. So now we got any doubt in this problem? You must be like him. He is asking many questions, right? So you must be like that. If you are not understanding, you must ask. Okay? So 270 volt we got, right? The terminal voltage. Therefore, we are boosting the voltage. 240 volt here substation. We are boosting it to 270 volt, right? Okay? Okay. So now your series generator is over. Now I'll talk about the compound generator. So already I talked about this in the previous classes also. So there are varieties of compound generators. One is your cumulatively connected, other one is your differentially connected. So cumulative means your series flux, or the flux produced by the series winding is aiding or supporting the main field winding flux, right? And differentially connected means your flux in the series winding will actually it will actually oppose the main field flux, right? So you can see here, this is what you are seeing here. This is a field pole. It is mentioned south pole. Okay. North pole is not shown, only south pole I have shown. So now in this pole, we can see here the current direction in the series winding, series field winding and the shunt field winding. Okay. So they are in the same pole structure. So what will be the flux direction because of the series winding? And what will be the flux direction in the because of the shunt field winding current? They're opposite. They're in the same direction and they're adding each other, right? So therefore this is cumulative. And next here I just made the current flow in the opposite direction in the series field, so it will just oppose, right?
Ah.
The filled flux, right? So therefore this is your differential compound motor, right? Now, so based on the connection of the shunt field, we can have another variety of cumulative generator, another variety of compound generator. One is when the field is connected at this point, where it is connected, you are seeing here, right? Near to the armature. And then we are connecting the series winding. Another structure we can make is, we can connect the field winding here, near to the load or after the series winding. So two structures we are seeing here, right? One structure is near to the armature, other structure is far from the armature. Now this structure you are seeing is, it is near to the armature, right? After this the series winding is connected, right? Another figure you can see here. Here this is your shunt field is connected after the series winding. But here what you are seeing, the shunt connection or shunt field is connected before the series, right? Series winding. So therefore, this is known as short shunt. Okay, this is also short shunt. Then what is the difference? There is a mistake here. Your dot will be here, right? So the difference is that one is cumulative,
One is differential.
one is differential. So therefore we can say that short shunt cumulative compound generator. Another view we can say that short shunt differential compound generator, right? So here we are showing the short shunt cumulative compound generator, right? And this structure is known as long shunt because your shunt field is connected after the series winding. So therefore I can say this as long shunt. Okay, this is long shunt. Okay, and cumulative differential, they will remain same. So only the difference is long shunt and short shunt. Okay, so now this is the structure. Now we'll see the characteristic. What we talked about till now, the external characteristic and the voltage regulation, of course, from the external characteristic you can find. So now we'll see the external characteristic. So here we'll summarize all the characteristic, whatever generator we have studied till now. We have studied shunt, right? Series, then your compound, right? Then separately excited, right? So here we can see here, this is your no load voltage curve, this dotted line. Okay, and now if your terminal voltage is remaining, because compound generator is designed in such a way that we can adjust the field in such a way that we can get the required voltage as per our desire. If at the load point, full load, we want to adjust the voltage, and we can achieve the no load voltage as well, right? So therefore, if the no load voltage becomes equal to the full load voltage in a compound generator, we call it flat compound. Okay, and if the no load full load voltage is greater than the no load voltage, we call it over compounded. Okay, and if the full load voltage is less than the no load voltage, it is called under compounded. Like, so under compounded, over compounded, and flat compounded, right? So now other characteristics are given. This is for shunt generator, this is for differentially. These three curves actually cumulative. These three curves shows for the cumulative differential generator, because in case of differential generator we cannot have such curves, over compounded, flat compounded. It is not possible because the series flux is opposing the main flux, right? But it is possible in case of cumulative by adjusting the series flux, we can get such characteristic, right? Now, in case of differentially compounded, we'll get this curve we are seeing here, right? This is for the differentially compounded. Now this is Sant, right? And of course, series, we told this is your residual voltage, then it will go up, right? So this is the characteristic we have seen. This is the external characteristic. Now if we'll see the characteristic in order to maintain the voltage at a particular voltage. Suppose I want to maintain the load voltage at no load, then what I need to do for all the generators, in case of all the generators, like my no load voltage, in case of shunt generator, the no load voltage will be higher, right? Like this one, right? This is for the shunt. And then for under compounded, this will be the starting point of the characteristic. Similarly, for the differentially compounded, it will be more higher, right? But in case of flat compound, where the no load voltage will start, again the full load voltage will be same. So that means your flat compound generator has the better voltage regulation as compared to other generators, right? And series, of course, we are saying this is the dotted line for the series generator, right? So this is how we can maintain the voltage for different generators at load, full load. Okay. Now this is your compound generator. Now we'll talk about the efficiency of the generator. So efficiency, we know efficiency is E out by P in. Very simple, right? Into 100 it will give me in percentage. Okay. Now I need to find the maximum efficiency criterion. That means I want to find the load, because at full load we may not get the maximum efficiency. So I want to find a load at which the machine will give me the maximum efficiency. Why this is important to know? Because when I know the point where the machine is giving the maximum efficiency, if it is operated around that point, then the losses will be less. By that way, the heat generated in the machine will be less, and the deterioration in the machine will be less. So the aging of the machine will be more, right? And also the efficiency, performance of the machine will be more. So therefore, always the machine should be operated in the maximum efficiency point. That means near to the maximum efficiency point, not exactly. So therefore, it is very important to know at which load the machine will give me the maximum efficiency. Okay. So already you know the transformer. In case of transformer, you have studied, right? How to get the load at which the transformer will give the maximum efficiency. What is the formula? Can you tell? Huh? Very good. Copper loss is equal to core loss. The same formula will get here only for the permanent magnet machine, not for others. Okay, let us see. Now let me consider a permanent magnet machine where PO, that is output power, is terminal voltage into load current, right? VTIL, and of course P in will be BTIL plus IL square RA. This is your PO plus IL square RA plus PR. PR is your rotational loss, right? That is constant. Now if we'll write the efficiency will be VTIL by the same approach what you adopted in case of transformer, the same approach will follow and will find, right? VTIL by VTIL plus IL square RA plus PR, and if I'll take the derivative of the efficiency and equate to 0, I will get this. Right, what it is showing? ILM square IRA equal to PR. So PR is your constant loss. That means if the machine is operating at constant speed, that will give me the constant loss, rotational plus magnetic loss, that is PR. that should be equal to ILM square. Here ILM indicates the load current at which the machine will give the maximum efficiency. Okay, ILM square RA equal to PR. Okay. Now this is the criteria, and using this criteria we will derive all others. This is for the permanent magnet machine. Okay. So now, if I'll find at what load, what percentage of load this will be the maximum, then of course from this expression I can find X equal to PR by P couplerless full load square root. That will give me the fraction of full load at which it will give the maximum efficiency, right? That means your full load, if your full load is 100%, like your 100 ampere, let us say, then if your X is found to be 0.7 from this expression, then at 70 ampere I will get maximum efficiency. Okay, it is clear, I hope, right? Now for the separately excited generator, we will get the maximum efficiency at ILM square RA equal to PR plus IF square RF. Can you derive this? Please go ahead and derive. So next we will see the shunt machine. For a shunt machine, it will be ILM square RA equal to PR plus IF square RA plus. This is little difficult rather than separately excited generator. So please do it in your home as a homework. It may come your exam, okay? And for series generator, this will be ILM square RA plus RS equal to PR. And for short shunt compound generator, it will be ILM square RA plus RS equal to PR plus IF square RA plus RF. Then your last one is long shunt. This is ILM square RA plus RS equal to PR plus IF square into RA plus RS plus RF. So please do it. No need to submit anything, but do it and practice it. And also do some problems on this. So this is here is a problem. If okay, yes. So everybody is taking snapshots. I am not discussing this, so you will do it. Okay. Okay. So please try to do it. This is a very simple problem, and long shunt. Okay. Okay. So we'll stop here, and next class onwards we'll start DC motors, because we took long time in this generator, and I hope these machines are very similar, and we'll quickly finish the motor part. Okay.